Hi everyone, today I'm going to talk about time dilation derivation in this video. So basically I'll mainly focus on derivation of time dilation equation, which is one of the Lorentz transformations equation that is crucial to the modern physics. So derivation of time dilation equation um, is derived using a system of time clock, which we can measure different distances and different times in order to come up with the equation. So firstly, we need to look at two reference frames, S prime and S. These two frames, their only difference is that one frame is moving with velocity v, while the other is stationary relative to another. So S prime frame is the frame that is moving with velocity v to the right. And we can see that there is a light source on the center, on the bottom, that emits the light to the top and then reflects. The light reflects and goes back to the bottom. And they travel the distance of 2d prime. As we set over here on the right, we can see that the distance between two mirrors is d prime. And then we can see another frame, that is S frame, that is stationary with respect to S prime frame. And again, we can see exactly the same setup, but with slightly different patterns of light, because S prime frame is moving with velocity v, but S frame is stationary with respect to this frame, which means that the light pattern that S frame sees is a very different pattern because it also has a horizontal component to its velocity. So we set the distance that the light travels diagonally to the top as d, and then we can observe that it travels the same distance as it comes back. And then the distance between mirror and mirror 2 stay the same, d prime. And then we set a new distance on the bottom, that is L, in order to make another observation that it's a right triangle, and we can use the Pythagoras theorem to come up with a relationship between d and d prime and L. So there are several equations that we need for the derivation of time dilation Lorentz transformation. So the first equation that we can come up with is delta t prime equals 2d prime over c. So this equation is from the first diagram that we saw up here, which explains the S prime frame. And as you can see that it's S prime, so it's natural that we set everything else with also primes. So we set the distance as d prime, and we set the time as delta t prime. So we can see that the amount of time that it takes to come back to its original source is actually delta t prime equals 2d prime divided by c, because it goes up and goes down, and the speed is c, because the light speed, the speed of light is the speed of light source. And the second equation, as you can see here, comes from the S frame, obviously, because there are no primes, and delta t equals 2d over c. So basically, we set the distance that the light source travels upwards diagonally as d. So we can see that the speed of the light source is c, and the distance that it travels one time as it goes up is d. So basically, the total distance that it travels is 2d, and the speed stay the same, so it's c. So the delta t is 2d over c. So another observation we need that is the equation for L. So basically, we can see that the L can be defined as in terms of horizontal velocity. So the light travels diagonally, so it has a horizontal speed that is parallel to two mirrors. So you can see that the light travels 2L with the velocity of v, which means that in order to get an equation of L, we can just divide two sides by 2, and then we get L equals v times delta t over 2. And then, as I said before, we can use Pythagoras theorem to come up with equation number 4, which is d prime squared plus L squared equals D squared. So this equation is pretty straightforward because we defined the distance between these 2 points. I can write here between these 2 points as L, and then this distance as D prime, and this distance as D. So we can basically easily come up with a using Pythagoras theorem, an equation that we can use to come up with the final result that we want. So using these 4 equations, so basically the first step here is to plug in equation number 1, 2, and 3 into 4. So after plugging in these equations, we can see that there's a common denominator 4. So we can actually cancel those, and we can make another observation that there are similarities of these 3 terms. We can see that they all share the similar form, right? Velocity squared times the time squared. And 2 of the terms have exactly the same term, so we can actually factor them out. So we can actually factor out the delta t squared part from the 2 terms that we have up here. Yeah, like this. So basically, after this, we can just divide c squared minus b squared on both sides, and we can get the equation in terms of delta t. And basically, what we want to do here is to divide. So we want to work with the equation on the right side, and we want to divide all terms, so numerator and denominator, by c squared in order to get rid of the c squared and get a pure relationship between delta t and delta t prime. So after dividing by c squared, we get this equation, and we can see that there are squares on both sides. So we can actually take a square root, and we get the simpler equation, which is delta t is the later time, and delta t prime is the proper time, and the whole term that we have, the whole numerator, the whole denominator we have here is called the Lorentz factor, which is a very important common pattern for Lorentz transformations, including length contraction, which my partner will talk about in the next video. So this whole thing comes up to a very crucial conclusion that that the Gaussian transformation doesn't work under a special system, which is when the object or anything travels near to the speed of light.
Hi everyone, today we are going to derive the length contraction. So before, we have the time dilation formula, which is delta t equals to delta t prime over the square root of v squared over c squared. Okay, in this situation, we know that this is you. You are in the s prime frame. You are moving with the speed v, velocity v with respect to me, and I am in the rest frame here, s here. Okay, let's define something. We need to define the proper time, which is the time difference between two events, the two events that occurring at the same position. And also, delta t is the time that I am measuring. Delta t prime is time that you are measuring. Okay. So now, suppose there is a rod here. first step is to define the event 1 and event 2, because we have to define what is the proper time. So let's suppose this is event A, this is event B here. A is here and event B is here. Okay, so point A is that you passes the left end of the stick, and event 2 is that you passes the right end of the stick. You understand? Okay, so the event 1 is you passed A. Event 2 is that you pass the point B. In your frame, you are moving with the speed, velocity v with respect to me. But actually, the event only occurred at that location. At this location, the position doesn't change, right? With respect to you. It passes A, event 1 occurs and event 2 occurs, but the position doesn't change. So, proper time you are measuring. So now we can begin to derive it. So first, we have L and L prime. The L is the length that I am measuring. I am in the rest frame and measuring the stick length, right? It's the length I measured. And L prime, which is the length that you measured. You measured the length of the L prime. You measured. Those two are totally different, are the same actually finally. We will get the same answer here. So we can do the L prime here first. L prime, let's recall that the displacement equals to what? Displacement equals to v times t, right? So in your raster frame, you are moving with the speed v with respect to me, right? But you are experiencing the dilated time, so which is the t prime. And also we have the time dilation formula, which is delta t equals to delta t prime over square root of 1 minus v squared over c squared. So now we got a v times delta t times square root of 1 minus v squared over c squared. What is that? This is the speed, the velocity we measured, and this is the time we measured, right? It's actually the speed. Why are those two speeds are the same? Because you are moving with the velocity with respect to me in a positive direction. But suppose you are in the rest frame. You are in the rest frame. I am moving with the speed, with the velocity, in the opposite direction v. The magnitude of those two velocities are the same. We don't care about the direction now. We now only care about the magnitude of those. So now we have L, the length that I measured, equal times square root 1 over v squared over c squared equals to the length you measured. So here, the length I measured, think about that. is actually the length of the rod of the stick, right? And that also equals to V times T, because we have the time dilation formula. We can get a V times it, delta T prime over square root of 1 over V squared over C squared. We have that. And what is V times over, what is that? What is that? This is the length that you measured, right? Those two are the same. So finally we can get L prime over 1 over the square root of 1 minus C squared. V squared over C squared. So let's think about that. Think about the term here. If V is greater than 0, which means an object is moving, so that term here is always less than 1, right? So the total term 1 over is saying that is less than 1. We can get a number that is greater than 1. So we can make a conclusion here. L equals to L prime times something that is greater than 1. What is the meaning of that? What is the meaning of the equation here? We can get a conclusion that L must greater than L prime. So here's the example. We have the equation here, and we also have the equation like this. L prime equals to L times 1 over 1 minus V squared over C squared, which is L times something that is less than 1. Okay, for the example 1, I will illustrate what means of the equation here. With respect to me, the distance between two homes is L. But actually, with respect to you, what is the distance from A to B? It's like, okay, because you are moving with a speed, velocity V, you are actually moving a smaller distance, which is L prime, between those two distinctions. And for the second example, I will show if the velocity is very, very smaller than speed of the light. Okay, we have the equation here, like, let me roll it down. L equals to L prime times over 1 minus V squared over C squared for 1, right? So this is you are running with speed V with respect to me, and so if V is really, really less than the C squared, we know that the C is the light speed is very, very big. So something that is big over 1, what is that? It is like 0, right? Approximately 0. So that equation becomes L equals to L prime over 1 minus 0. So this is approximately L prime times 1 over 1, which is L prime. There is no difference between what I see the lens and you see the lens. This is when when the velocity of u with respect to me is approximately the times the light speed, so we can get the equation here. L equals to L prime times 1 over something that is very small, so we get a L prime times something that is very big. So L equals is no more equals to L prime, right? That doesn't, so yeah, the length is actually contracted. Let's see why. L with respect to u, the L doesn't change, right? So the L prime must be very very small, so that it times a big thing to make it equals to the L, which is the length that we measured in the ref frame. So we have the definition for the proper length, which is the length that we measure in the ref frame. Okay, in summary, like we derive the time dilation and length contraction step by step with some detailed examples. So thank you guys for listening, and thank you for watching this video.